And I am recording, Cheyenne. Okay, so here's where we kind of left off. Attention, please. Excuse me. Okay, so on 2-3, we kind of left off. What we really did, we just did two important things. We did the product rule and the quotient rule, and you've been busy practicing that, which is great. The rest of the chapter is no harder, maybe easier. The section, excuse me, is no harder, maybe easier than that. All we're going to do for the rest of the section is we're just going to add a couple of trig derivatives, the missing ones, right? All we've really got are sine and cosine. So we'll add the other ones in there, and you can practice using them, and that's really it. There's nothing more beyond that. So we're gonna go ahead and derive the tangent derivative, though. You're gonna do it. Okay, you're gonna walk. You tell me what to do. I will be your gopher up here, and you just tell me what to write. So what we want to come up with, your Shreve. I'm just a grunt. I will do. You tell me what to do, and I will do it.
Is this the last one?
This is what we want to come up with this derivative rule. That's our one of two goals for today. Okay. So suggestions. How can we approach this? Yes, Clancy, what do you think?
Break it into sine over cosine.
Okay, break it into sine over cosine, but I'm gonna wait for, I still hear some. Okay, break it into sine over cosine. Excellent idea. That's always our strategy when we're working with the composite trig functions, right? We know how to deal with sines and cosines. So this is really just equal to the derivative with respect to x of sine x over cosine x, and we now are equipped to deal with that derivative, aren't we?
Yeah.
Okay, Hunter, what is that? What kind of rule are we gonna have to apply to that derivative?
Oh,
Quotient rule, sure, right? We've got a quotient of functions. U, in this case, is sine x, and v is cosine x, right? But all we're gonna do is just the quotient rule. So, take me through the quotient rule then. The quotient rule is what, Julie? Without looking, what's the quotient rule?
U times v prime minus v times u prime over v squared.
Agree? Hunter's shaking his head. I think you might have gotten the first part mixed up.
That's b times u prime minus u v prime.
Okay, good. Over
v squared.
Okay, good. So it's the bottom, which we usually call v. The bottom times the derivative of the top.
Minus the top times the
We all set? Okay. The bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared, right? Usually we think of it in terms of u's and v's. So let's do that. So then we said bottom, right? Times, I gotta go red for my derivative. Derivative of the top is what? Positive or negative? Positive. Positive. Good. Times the derivative of sine x is cosine x. Good. Minus the top. Good. So minus sine x times the derivative of the bottom, which is negative sine x. Very good. Okay.
Cosine x squared.
Good. Over cosine squared x. Very good. Okay, so cosine u. Okay, good. Minus uv. Very good. Okay, so what can we do with that?
Simplify.
Yes, sir. What do you think?
Combine the cosines and sines, so you get cosine squared x minus sine squared x.
Okay. Okay. So yeah. So we're gonna get cosine squared x minus sine x times minus sine x is
Plus sine x.
plus sine squared x over
Cosine squared x.
cosine squared x. Okay. Does anybody recognize something tricky going on here? The trig idea. Okay. Now that's true. Okay. I can't I can't cancel those because they're not common factors. But what about the top?
It's equal to 1.
It's 1. Yeah, that's our Pythagorean trig identity, right? For sines and cosines. So we know sine squared x plus cosine squared x equals 1, or vice versa. So we get 1 on the top divided by cosine squared x. Now what is cosine x? Excuse me, 1 over cosine x is secant x, isn't it? So does everybody agree that, technically I probably need to do this. I could write this as 1 over cosine x quantity squared, right? But we could skip that step, really. What are we going to get for our answer?
Secant squared.
Secant squared x, right? I'm going to get a secant x squared, which is really just secant squared x. And I would say that we could have really just skipped right from there to our answer, which is secant squared x. So we've got it. The derivative of tangent x is equal to secant squared x. We got a new rule. Okay, yeah, so now let's take a guess. Let's take a guess here. Well, actually, I'm not going to have you take a guess yet. We'll take a guess momentarily. Yes, ma'am?
Why don't the cosine squared x cancel out?
Because that would be improper to do, because I can't, cosine squared x on the top is not a factor. It's a term, right? So here's an example. So we could cancel, like if I had, for example, a plus b over a, I can't cancel those a's, right? That is not equal to 1 plus b, right? That would be a no-no. Okay, but I could do this. If I had a times 1 plus b over a, because those are factors, I could cancel those. Right? Thank you. Does that make sense?
Yeah.
Okay. So one more. Let's go. Let's try. How about if we just do secant? We'll try doing secant. So if we have the derivative with respect to x of secant x, what am I going to do?
1 over cosine.
Good. So I'll write that as in terms of sines and cosines. That's just 1 over cosine, isn't it? Right. So I've got the derivative with respect to x of 1 over cosine x. Okay. So do I want to use the quotient rule there?
No.
You're right. I do not, because I don't have a quotient of functions. I've got a constant on the top. So what do I do instead? It's kind of tricky.
It would be like 1 over negative.
Okay, I can't do that either, because I don't know.
It would be like cosine x to the negative.
Okay, good. So now compare this to, what would we do if we had, for example, just a non-trig derivative to do? What if we had the problem y equals 1 over x, and I want to find y prime?
X to the negative.
Yeah, right. I would just write that as x to the minus 1 and use the power rule, right?
Yeah.
Do you agree? Much easier than the quotient rule. So I'm going to do the same thing here. So I'm just going to write this as the derivative with respect to x of the quantity cosine x to the minus 1. You know what? It just occurs to me that this is probably not a good one to do for right today.
So how about you just do us against it?
Yeah, okay, because today, if I do this today, I've got to use the quotient rule, and I do not want to. So I am just going to give you the answer. We'll come back and look at this in a better way during 2-4. It'll be easier to do, and it'll make more sense. We could do it, but I don't want to train you to do something that I later don't want you to do. So we're going to skip this one. So I'm just going to make our list. Here's our list of trig derivatives. We're just going to fill in the blanks. So we know here that the derivative with respect to x of sine x equals
Cosine x.
cosine x. Okay, now I'm going to partition these in a way to help you establish a pattern. I'm not going to tell you what it is right now. We also know that the derivative with respect to x of cosine x equals negative sine x. Okay. We know that the derivative with respect to x of tangent x equals
Secant squared x.
secant squared x. Okay, I'm going to tell you another one. I'm going to tell you that the derivative with respect to x of secant x is equal to secant x tangent x. Okay? And we'll derive that later. Okay? It'll be easy for us to do very shortly. Okay, anybody want to make a guess what the derivative of cotangent x is going to be? Okay, I heard cosecant squared. Almost. Negative cosecant squared x. Okay, does anybody care to hazard a guess as to what the derivative of cosecant x is going to be?
Negative cosecant x.
Okay, do you see a pattern? There's a symmetry there, isn't there? There's a symmetry. We know that, I would claim that if you just know the three derivative rules on the left, you automatically also know the three derivative rules on the right. Okay, because wouldn't you agree that the only pattern here really is just that the normal trig functions and the cotrig functions are just interchanged from left to right, aren't they? So up here, instead of the derivative of sine equals cosine, we get the derivative of cosine equals negative sine. The sines and the cosines just exchange places, right? What about here? The derivative of tangent x as compared to the derivative of cotangent x. Well, if this answer, the derivative of tangent x is secant squared x, then because of our symmetry, the derivative of cotangent x must be the co-equivalent of secant squared x, cosecant squared x. But whenever we differentiate a co-function, we always get a negative answer, right? Okay. The derivative of secant x is the product of secant x and tangent x. Therefore, the derivative of cosecant x must be the product of the co-equivalents, right? Cosecant x times cotangent x, but times negative 1. Because whenever we differentiate a co-function, we get a negative answer, right? Make sense? So you really get 6 for the price of 3. That's a pretty good deal. And really the rest of the chapter is just about using those. So let's practice using those a couple times. Let's try, let's see. Okay. Couple things I want to look at here. So, how about this? What if I give you something like this? Okay, we want to find y prime. Okay, what do we do? What do we do here? What are our options? Quotient rule? Okay, so should we just jump in and use the quotient rule? Maybe not. Okay, this, we're getting to the point now where we're starting to reach that point in the class where jumping blindly into doing math is a bad idea, because that can lead you down some seriously bad paths. I can remember, here's a little anecdote. This is just to illustrate kind of the other end of this end of the spectrum that you're kind of working towards. I had a quantum mechanics problem set. Have I told you this story?
No.
I had a quantum mechanics problem set in college that was, I still have nightmares about this to this day. We had weekly problem sets in all our physics classes, you know, and this one had 3 problems on it. Doesn't sound half bad, right? Okay, I'm not kidding you. When I was done with that, just the work to solve those 3 problems took almost 200 pages of solid symbolic math. Okay, I think I did that a fairly good way. I mean, there's people that did it in better ways, but it wasn't a bad approach. But if I hadn't really, and it took like 40 hours. Oh, this guy was just such a jerk.
40 hours?
Yeah, it was terrible. This guy hated
Were
this
you
guy.
awake
It was
the
terrible.
next day.
It was horrible. It was a week-long problem set, but it was just terrible. My class was, that's a nightmare about it. But anyway, if I had so carefully thought about how to do this and picked a good method, there is no chance I would have ever gotten through that problem set. Because you just absolutely have to, as you get into more complex stuff. You just have to think about, okay, not just what can I do, okay, but what can I do to make this problem A, doable, and B, doable in a way that's not gonna, drive me crazy, right? So you really gotta start to think about these things strategically. You can't just mechanically jump in. You've always done that in the past because you're so smart. But now we're getting to a branch of mathematics that's got too many paths to take. You gotta pick the good one. So this is a very lightweight example of that, but we could just jump into this with the quotient rule. And it wouldn't be horrible. You're not gonna spend 40 hours doing that problem. But that, it's quotient rule is not fun to do, right? Okay, what else could we do with this? Suggestions? Well, I can't really because I don't have stuff squared up there. If I had 1 minus cosine squared, that would be great because then it would be sine squared and make this really simple. What do you think, Jane?
Can you simplify the cosine versus sine?
Yeah, why not split this into 2 fractions and it gets really simple. If I split this, now this is something, and this is part of, once again, this is kind of reinforcing my statement I made at the beginning of the year that you will learn more algebra in 1 short year than you have probably learned cumulatively in all of your math careers in calculus. You will get to be very good algebra students because we do so much algebra as a part of doing the calculus. So what do? If I have a common denominator, I can split those fractions, right? So if I do that, if I split these fractions up, I get 1 over sine x minus cosine x over sine x, aka, what's 1 over sine x? Cosecant x minus cotangent x, good. And so that is trivial. Those are just standard rules, right? The derivative of cosecant, now it might not seem trivial to you at this exact second because I just showed you that rule, but within about, I'm going to estimate about 37 hours from now, that's my estimate, at that time, you are going to say, oh, I know those trig derivatives so well. Those are answers that just immediately spring to mind and you don't have to do anything. This is just a standard answer. What's the derivative of cosecant?
Negative cosecant cotangent.
What's the derivative of cotangent? Okay, so I'm subtracting a negative makes it plus. Done. How simple was that?
Got your answer?
That's our answer. Yeah. Right? So it's much, much easier if you pre-write the problem in a way where I don't have to use any complicated rule. I can just use simple standard rules, right? Okay? Let's do another one.
And then we're done.
Yeah.
Are we really?
I mean, this is kind of what we're doing, yeah. So let's try this. What about, I'm gonna make one up. I don't like it.
Hey, Mr. Oya.
Yeah.
I'm just thinking about your big problems and well, like your math ones. And what did it even look like? Like, what did the problem look like?
Oh, the problem was, we had to derive from basic principles, kind of the quantum state of a hydrogen atom. So it was, it was not very fun. I had to literally read a whole book that week that was never signed just to understand what I was doing.
Oh my
It was
God.
terrible, yeah.
How many years did you go to school and what year were you doing that?
That was when I was at Stanford. Yeah.
Oh, so I had that.
So I was there for 4
That
years.
wasn't like a freshman level.
No, but it was a junior level class. But it was honestly, it was a graduate level class that were juniors.
Okay, thank you.
And you did physics major, right?
What's that?
You did physics major, right?
Yeah, I did, yeah.
Yeah.
Times.
Like if you didn't do a science thing, you
No, times. Okay, what about that one?
You can.
Derivative of it?
Okay, so what are our options? I could use what rule? Okay, product rule. Or any other suggestions? Just stare at this for a second. Jenny's got an idea again.
I don't know if this is right. Would you like do like sin x over 1 and then 1 over cos x?
Ah, okay, yeah. What if I rewrote secant
You are
x?
so smart.
What is secant x? 1 over cosine x. And so if I multiply sine x times 1 over cosine x, what's that? Tangent x. And derivative of tangent x is what? Secant squared. Yeah, we're done.
Ginny, you are so smart.
And then I
Okay.
the numbers.
Put your brain in my brain.
Okay,
I don't know how I
good.
did it, but I did it. So.
Wow, this sounded easy.
Nope, don't
Don't
say
say that.
Knock on wood.
Maybe for Simon, you'll be like.
Oh, is that what somebody's doing an evil laugh?
No, they heard the evil laugh.
You guys all feel right?
No, you guys just ready to. Weird.
Okay, what about that one?
Oh, that's 2 terms.
Yeah, I can do this.
Okay, so this one, is there an easier way to write this one?
Probably.
Not so much. This one we're kind of stuck with. So what is this rule?
We have to do the quotient.
It's a quotient rule, isn't it?
Thanks.
Yeah. Okay. So I'll tell you what we'll do. Let's just do the calculus and then we'll make a decision if we really want to simplify this at that point. Okay, so y prime equals, what's the rule?
U prime minus du prime over v squared. I did that one.
Backwards.
It's
V u prime minus u v prime. Remember, it's the bottom times the derivative of the top minus top times derivative of the bottom, right?
Right.
Okay, so, and that's, remember, who was it that was, Sydney was, she had a little mnemonic device, which is low D high minus high D low, right? Low D high minus high D low.
I've never understood that.
So low D high, so here's gonna be D high. What's the derivative of the top? Derivative of 1 is 0. Derivative of cosecant x.
Negative cosecant times cosecant.
Minus high, oops, cosecant. D low, what's the derivative of the bottom?
Just positive.
Yeah, I'm gonna get 0 minus negative cosecant x cotangent x, right?
Which is positive.
Positive. So I don't need the plus sign, do I? Divided by,
1 minus cosecant x squared.
okay. So that looks pretty bad, but do you see anything potentially happening there?
Yep.
Can we cancel?
Yeah, looks like there's maybe some stuff gonna cancel, right? So I'm gonna get, let's see, I'm gonna get, if I distribute all this stuff, I'm gonna get negative, if I'm gonna distribute this over that stuff, right?
Oh, wait, why?
Now look what that's gonna give me. I'm gonna get a negative cosecant x cotangent x plus cosecant squared, everybody agree? I'm multiplying cosecant times cotangent. So I'm gonna get cosecant squared x cotangent x. Everybody agree with that first part?
Yes.
Okay, now let's do the rest. So if I distribute the -1 all the way through, I'm gonna get minus cosecant cotangent minus cosecant squared cotangent x, right? All over 1 minus cosecant x quantity squared. Well, something good happened at least. The cosecant squared x, cotangent squared x terms cancel, right? And these add, these are like terms, aren't they? I get negative cosecant x, cotangent x minus another cosecant x, cotangent x. What's that? Good. Okay, so I get negative 2 cosecant x, cotangent x over, and that's about as far as we can go, right? Okay, we're not going to get.
How do we know that? That's what I have so much.
Okay, yeah, so how do we know that? Can somebody explain how do we know that we're really not going to be able to do anything else with this? Yeah, there's no, well, okay, there's no other like terms to combine. And on the bottom, if I expand this out, the bottom has two factors. It's just 1 minus cosecant x times 1 minus cosecant x, but I don't have any of those factors on top to cancel, right?
Yeah.
So we know then that there's really nothing else I can do to this,
Okay.
okay? There's no way I can cancel factors or make stuff add to 0, so we're just done.
Is there an easier way to do that?
No, that one, and let's make sure we understand why. This one was different because there wasn't a tricky way to pre-write this, right? Now maybe if on the bottom, if I had just had like a cosecant x, yeah, we could have done it, right? Because 1 over cosecant x would have just been sine x, and cosecant over cosecant x would have been 1. But unfortunately, I didn't have that. I had a 1 minus cosecant x, and splitting that fraction doesn't do anything for me, right?
If you multiplied by the conjugate and then took the derivative, could that work?
Well, okay, I mean, there's always a possibility that if I multiplied by the conjugate, something might work out. I might get some trig identity that's gonna get us someplace. I don't necessarily think so on this one, and here's why. Because let me remind you, here's just a real quick review of the Pythagorean trig identities, because this is something we're gonna work with. So we all know, it's really simple, very, very simple. Don't remember these, you'll forget them. I never remember them. If you ask me now, I'd have to derive them for myself. I never remember, except this one. I know that sine squared x plus cosine squared x always equals what? 1. Okay, so then there's two ways we can go with this. I could divide both sides of that equation by sine squared x to get another Pythagorean identity that's going to involve ones and cotangents and cosecants. Or I could divide both sides by cosine squared and get the other trig functions, right? So let's do those. Let's say we're going to divide both sides over here. We're going to divide both sides. Divide both sides through by cosine squared. Okay, what am I going to get from this?
Sine squared.
Okay, right, I'm going to get, when I split the fraction, I'm going to get a tangent squared x and a plus 1, right? Okay, so tangent squared x plus 1 equals, okay, good. So that's good. That's one of our 3 Pythagorean trig identities. That's the one that links tangent and secant, okay? So that's good. There's 1, there's 2, let's get the third one. So the third one we would get by dividing both sides by sine squared x. So on this side I get 1 plus cotangent squared. I'm going to write it in this form. I'm just going to flip those around so it looks similar. You okay with that? Equals. Okay, there's all 3. So now you can kind of see why that's not going to work maybe. Because, let's see here. Maybe I'm wrong with that actually. What do we have on the other cosecant? So, yeah, it's probably not going to help us much, Right? And it's a good idea, but it's probably not gonna help us, because if we multiplied, we'd wanna get the bottom simplified. If I multiplied by 1 plus cosecant x on the bottom, I'm gonna end up with a 1 minus cosecant squared, which is gonna give us negative cotangent squared, right? But then on the top, we're gonna get a mess. And on the top, we're gonna get a bunch of cross terms. We're gonna get the cosecant squared, but we're also gonna get a 2 cosecant, see what I'm saying? So probably that's not gonna do us well, but it's a great idea, I mean, it wasn't bad, and sometimes that'll work. Sometimes that's something that will end up being a good thing to do. Okay, last one, and then I think we got this thing licked, and you can just work on this stuff tomorrow. Yeah. Yeah, sure.
Are those like extra derivatives?
No, these are just trig identities.
Okay, so they use those like they showed up.
Yeah, okay, one more time. All this was for, this is just how if you start with this simple trig identity that y'all know, you can easily get to these two by just dividing both sides by either sine squared or cosine squared. Okay, yeah, yep.
So if we see one of those little things in our like math when we're doing it, that we can just simplify it and use them.
Right, you can use them, exactly. These can be useful, so we could always trade, like a tangent squared x plus 1, we could freely trade for a secant squared, which might be useful. Okay. Yeah. Okay, so how about this? What if we've got, I want you to find the equation of the tangent line. Okay, here's your function. So we've got okay, so let's find the equation of the tangent line. And we don't have to find the normal line. You just tell me how we could do it once we find the tangent line. Let's find the equation of the tangent line to f of x at that point. So what are we going to do?
Oh gosh, I don't like that.
Okay, good. Think about the recipe. If I want to come up with the equation of a line, what do I need? A point and a slope, right?
True.
I've got a point. I just need a slope.
Yep.
I just need the slope of the tangent line, right? So isn't that going to come from the derivative? So what's the derivative of that function?
Secant squared x.
Secant squared x, good. Okay, so then the slope of the tangent line is really just the derivative evaluated at that point, right?
Wait, we said it again.
So the slope of the tangent line, remember what the derivative function does. The derivative function, when we differentiate a function, we get back a derivative function that's very powerful. That tells us the slope of the curve for any value of x we choose. Now, if we're trying to find specifically the tangent to the curve at this point, then we want to know what the slope of the curve is at that point, because that's going to be the slope of the tangent line, right? So we're going to evaluate this derivative function at this point in particular to find out what the slope is there. Now, at a different value of x, we would get back a different slope. Okay, does that make sense?
Yeah.
Okay, so then the slope of the tangent line is our derivative function evaluated at this point, because this is the point of tangency. And so that's just secant squared of pi fourths. Well, I never remember what secant is. I always have to turn it into a cosine. It's the reciprocal of cosine. What is the cosine of pi fourths?
2 or 2.
Square root 2 over 2, right? Everybody agree?
We can read that during how you find that.
What's
Oh,
that?
is that from the 45?
Unit circle.
45?
Yeah.
Did he just say
Oh,
yes?
yeah.
It's from the unit circle, right? So pi fourths is right there.
Wait, what?
We can use the triangle to find it, right?
Yeah, you can. That's fine. I would recommend. I think the unit circle is great. I think that's the best way to do it. Well, obviously, I need to take you through my unit circle too. Not today. Not today. Not today.
Yeah, because maybe we should, because I don't know it. Yeah, I just know it.
You'll remember it?
I know how to use it.
Okay. Yeah, some other time. Absolutely. Okay, here we go. Back. We're reeling you back in. Here we- So. So the cosine and the sine at this angle both have values of square root of 2 over 2, right? So then this is, so the secant, really all this is just 1 over the cosine squared of pi fourths. So that's just 1 over the square root of 2 over 2 squared, right?
Yeah.
Okay, let me pause. Everybody with me?
Sure.
Right? All I'm doing is I'm just evaluating what is the secant of pi fourths squared. The
Yes.
secant of pi fourths is 1 over the cosine of pi fourths. Cosine of pi fourths is the square root of 2 over 2 from the unit circle.
Yes.
Right? So what is the square root of 2 over 2 squared?
2/4.
2/4.
1/2.
So I get 1 over 1/2, which is what? 2.
Wow.
So the slope is 2. Okay? Right?
Yeah.
The slope is 2. That's my point. Now it's all downhill. Now it's algebra 1. Right? Now we can just say, we need to solve for b, right?
Yeah.
So we can use these points. We can say y equals,
MX plus B.
yeah, good, 2m times x plus b, solve for b. So what do we get? Pi over 2. So b equals 1 minus pi over 2. Everybody agree?
What did you just do?
Okay, so I just did this. Let me go back a little bit. Probably. Oops, too far. Okay, so this is the same thing as saying 1 equals pi over 2 plus b, right?
Yeah.
Okay, so b equals 1 minus pi over 2,
Oh, I see what you're saying.
What is that? 1 minus.
right? That's b. We already know m is 2, and so therefore the equation of the tangent line is just y equals mx plus b. That's it.
So that's the, what of the what?
That's the equation of the tangent line, right?
Yeah.
Okay, let's, tell me when you're done writing, and I'm just gonna, let's go back and just look at what we did. In hindsight always helps. Okay, we good?
No,
Say it again.
use that point.
Yeah, you could. You can use point slope if you want to instead. That's fine.
Okay, I'm ready.
Okay, so all we did, one more time. So I want you to see the strategy. The little, the little individual pieces are not a big deal. You'll practice doing those, but the strategy was, if this is the function and that's the point, to find the equation of the tangent line, we've got a point, we need a slope. The derivative gives us the slope. So we differentiate f, get f prime of x, to find the slope of the tangent line at this point. We need to evaluate the derivative at pi fourths, which we did, and we got 2 as our answer, right? Now we're done with calculus. From that point forward, we know the slope, we need to find b, which we did. You can use point slope formula if you want to. I always just use y equals mx plus b and solve for b. Either way, doesn't matter. Solve for b, and now we know b, we know m, y equals mx plus b. Okay. What if we wanted to find the equation of the normal line? Do we have to redo all the calculus?
No,
No.
perpendicular.
Yeah, we know that if the slope of the tangent line
-1/2.
is 2, then isn't the slope of the normal line?
-1/2.
Yeah. Negative 1. So I'd have to go back, and I would have to go back and find b again, wouldn't I?
Yes, you
Right.
would.
Okay.
4 minutes left.
What's timing? I'm done. Oh, and then the other thing they go through in here, you already know how to do. Higher derivatives. Right, higher derivatives are easy. If I want to find a second derivative, what's a second derivative?
Just keep going.
I like
Derivative
that.
of the third
It's like
derivative,
a
first
fun
derivative.
puzzle.
Yeah. Okay, I will show you one last thing. It's not just notation, so you're not confused when you see the notation. So we know that, yeah, if I want to calculate the second derivative, right,
Yes.
all that is just the derivative of the first derivative, right? A couple ways we can write that. I can also write that as d squared x over dy squared. That's a weird way to say it, but that's one way to write it. What might help you think of it that way, this isn't the way we normally write it, but this is what it means. Isn't it just the derivative with respect to x of dy dx?
Yeah.
That's why we get that weird notation, d squared x over dx squared, kind of, right? That means second derivative. We can also write it as y double prime. What happens if we get further down the line? Well, we could write, if we have a third derivative, we would just put an extra prime there. But I think after third derivative, it starts to be too many primes. Yeah. So then we would just write in parentheses, yeah, to mean it, right?
Got it. Thank you.
Okay, that's it, but otherwise, you already know how to do that. It's easy.
Yeah.
So when it gets to the fourth prime, you just start writing.
You just, yeah, then you just start writing numbers in parentheses.
I can't
Just because the primes get too, it's too hard to read, count the primes.
I mean, just start doing rows here.
That's just what they do, I don't
I
know.
know, that's funny.
All right, I better take roll.